Hello and welcome back to the Deep Dive. We are back with another session, digging through the textbooks and the notes to decode the topics that usually cause a bit of panic before the board exams.
Indeed. And today we're opening up a very specific, very crucial chapter of organic chemistry.
We are talking about Unit 6, halalocanes and haloarenes.
Specifically, we are focusing on their chemical reactions. And I have to say, this is the chapter where organic chemistry really shifts gears. You can't just memorize things anymore.
No, you can't.
You have to understand the logic, or you will get lost.
Absolutely. It's where the subject goes from what is this to how does this behave. Yeah. But before we dive in, I want to start with a little puzzle.
Okay, I like a good puzzle to start. Let's hear it.
Okay, so picture this. You're in the lab. You have a halocane, let's say 2-bromobutane. You add potassium hydroxide, KOH. Now, KOH is a base, right? It gives you that electron-rich hydroxide ion.
Correct, the OH- ion.
So the logic says this hydroxide should just attack the carbon, kick out the bromine, and swap places. You should get an alcohol. Simple substitution.
That is what you would expect. It's the most straightforward reaction, isn't it?
But here's the twist. If you take that exact same KOH, but this time you dissolve it in alcohol instead of water, and you heat the mixture, you don't get an alcohol.
Not at all.
The molecule, it sort of self-destructs. It kicks out a hydrogen and the halogen, and you end up with an alkene, a double bond.
So the same reagent gives a completely different outcome.
Exactly. Why does it sometimes swap and sometimes just rebuild itself into something new?
That puzzle is the perfect entry point. It really highlights the fundamental tension in this chapter, the battle between substitution and elimination.
Renovating a house versus knocking down a wall. I like that.
And that's our mission today, to decode the chemical reactions of haloalkanes, so you aren't just guessing on the exam paper.
And why should you care? Well, it goes beyond just the exams.
Oh, absolutely.
Yeah.
Think about synthesis planning. If you are a chemist trying to design a medicine, you have to create a specific bond. If you don't understand these rules, you might accidentally turn your expensive material into a useless gas.
Just because you pick the wrong solvent.
Exactly. It's all about controlling the outcome.
So let's start at the very, very beginning, the simplest explanation. I like the idea of a halocane as a loaded spring.
That's a very good analogy.
Yeah.
It all comes down to the CX bond, the carbon-halogen bond.
Right. And halogens, chlorine, bromine, they're very electronegative. They pull electrons towards themselves.
Correct, which leaves that poor carbon atom feeling a bit positive, electron deficient. It's under tension.
So it's just waiting for a trigger to release that tension.
Yes. And depending on that trigger, the nucleophile, the solvent, the temperature, that spring releases in one of three ways.
Let's list them. First, we have SN2.
The direct displacement, one step, bam, done.
Then SN1. This is the slower one, right?
Yes, this is where the halogen leaves first, creating a gap, and then the new group enters. A two-step process.
And finally, elimination. E1 or E2, the one from our puzzle.
Where a hydrogen is removed, and the molecule completely changes shape to form that double bond.
Okay, to make this really stick, let's try a visualization.
Good idea. If you can, just close your eyes for a moment. Picture that halocane molecule.
Okay, I have it in my mind.
For SN2, I want you to visualize a strong attacker, your nucleophile, hitting the molecule hard from the back. It pushes the halogen out the front in one smooth, powerful motion.
Like a billiard ball collision.
Exactly, one in, one out. Now for SN1, picture something else. The halogen just gets tired. It decides to leave on its own.
It just detaches.
It just leaves. Now you have a carbon atom left behind with a positive charge.
Right.
That's your carbocation. It's just waiting there. And then a new partner comes along and joins it.
So one is a crash, the other is a waiting game.
Precisely. And that leads to the technical terms. SN2 is bimolecular because two molecules, the attacker and the halocane, are in that crucial step.
So the rate depends on both?
Correct. But SN1 is unimolecular. The rate only depends on the one halocane molecule breaking apart. The attacker is just waiting, so adding more of it doesn't speed things up.
That makes a lot of sense. So let's bring in the anchor definition, the one you need to write for the exam.
Right. The insert safe definition is, haloalkanes undergo nucleophilic substitution, SN1, SN2, and elimination, E1, E2 reactions, with the dominant pathway determined by carbon type, leaving groupability, nucleophile-based strength, solvent polarity, and reaction temperature.
Okay, that's a mouthful, but it covers all the triggers we talked about. Now, we have to fix a big misunderstanding.
Ah, yes. The most common trap.
The idea that all haloalkanes react the same way.
No, not at all. The structure of the molecule itself is the most important factor. Primary, secondary, and tertiary haloalkanes follow completely different pathways.
This is so crucial. A primary one prefers SN2. A tertiary one prefers SN1.
It dictates everything.
To really get this, let's use another analogy. The fortress.
The fortress. Okay, let's build it.
So imagine the haloalkane is a fortress. The central carbon is the king inside, and the halogen is the gatekeeper at the front door. We want to conquer this fortress.
And we have 3 strategies.
Strategy 1, SN2, the direct assault. An elite team, that's your strong nucleophile, doesn't attack the front gate. They go around to the back.
The backside attack.
Exactly. They hit the rear wall, and the force kicks the gatekeeper out the front. But this only works if the back is open, which is a primary carbon.
Right. If it's a tertiary carbon with 3 other groups around it, the back is blocked.
The elite team can't get close. Steric hindrance. The assault fails.
So what's strategy 2 for that crowded fortress?
That's SN1, the siege. Here, a large army, a weaker nucleophile, just waits outside. They don't attack.
They wait for what exactly?
They wait for the gatekeeper to quit. In a stable tertiary fortress, the king is secure, so the halogen just leaves on its own. The fortress is empty for a moment.
And the carbocation is formed.
Exactly. Once it's empty, the army just walks in. This only works if the fortress is strong enough to stand empty for that moment. A primary one is too much for that.
So, assault for the open primary fortress, siege for the strong tertiary one. Brilliant. And the third strategy.
Elimination. The tunnel. Now, you have a tunneling expert, which is your base. They don't try to get inside. They dig under the wall.
They remove a hydrogen from the outside.
Yes. And the foundation crumbles, the defenders escape, and the whole fortress transforms. It forms a double bond.
And for the tunnel strategy, you usually need
Heat. You need that extra energy, that chaos, which favors breaking one molecule into many smaller pieces.
So without this concept, we'd be lost, wouldn't we? We'd just be mixing chemicals and hoping for the best.
You'd never be able to predict if you'd get an alcohol or an alkene.
Okay, so let's run some actual lab experiments, the kind where they ask, what do you see in the exam? Let's start with a clear SN2 reaction.
Let's do it. We have 1 bromobutane, a primary haloalkane. We add aqueous KOH.
Aqueous is the key word. Water as a solvent.
Right, so 1 bromobutane is an oily liquid. As you heat it gently, you see the oily layer starts to disappear.
Why does it disappear?
Because it's converting to 1-butanol, an alcohol, which is soluble in water. It just dissolves. It's a clear sign of substitution. Primary carbon, strong nucleophile, direct attack, SN2.
Perfect. Now for SN1, this one is more dramatic. Let's take tert-butyl bromide, a tertiary one.
And we use our special reagent, silver nitrate.
The halogen detective.
It is, and the observation is immediate. You mix them and boom, a white precipitate forms instantly.
That precipitate is silver bromide. It's proof that the bromine has left the molecule.
The silver forces the siege, it pulls the bromine away, the stable tertiary carbocation forms, and the reaction happens fast.
A classic SN1 indicator. Okay, last one. Elimination. Let's take 2-bromobutane, the tricky secondary one.
The one that can go either way.
Yes. We add KOH, but this time it's alcoholic KOH, and we heat it strongly.
And what's the observation? No disappearing oil, no precipitate. Instead, you smell something. A sweet, pungent smell.
The smell of an alkene, butene gas.
Exactly. The high temperature and the strong base favored the tunnel strategy over substitution. You made a double bond.
And chemists use this control in the real world, right? To make drugs.
All the time. Let's say you need to make an ether for a drug. You have to be so careful. You choose a specific polar protic solvent to force the reaction down the SN2 path.
Because if you don't,
you'll trigger elimination and end up with a bucket of useless alkene gas instead of your medicine.
it's high-stakes cooking, really.
Yeah.
Okay, let's distill this down. We need some exam-safe clarity lines.
Yes. The sentences to memorize.
Clarity line 1. SN2 is favored by a strong nucleophile, a polar aprotic solvent, and a primary haloalkane.
And the tieback. Primary is open, the back door is unlocked.
Clarity line 2. SN1 is favored by a weak nucleophile, a polar protic solvent, heat, and a tertiary haloalkane.
And the tieback here is that the tertiary is too crowded for a direct attack. It has to wait for that carbocation to form.
Clarity line 3 for our starting puzzle. Strong bases plus high heat favor elimination. E2.
And remember, don't confuse a base with a nucleophile. A base wants a proton, a hydrogen. Heat loves the chaos of elimination.
Clarity line 4. Zaitsev's rule. In elimination, the major product is the more substituted alkane.
In simple terms.
The double bond prefers to form in the middle of the chain, not at the very end. It's more stable there.
Got it. And the last one about the 3D shape. This is a favorite for competitive exams.
Yes. Clarity line 5. Stereochemistry. SN2 causes inversion. SN1 causes racemization.
Inversion is the umbrella flipping inside out.
Precisely. The backside attack flips the molecule's configuration. But SN1 creates a flat intermediate, so the new group can attack from either side 50-50. You get a mix of both forms.
You lose the optical activity.
You do. It's called a racemic mixture.
Okay, let's bring it all home. A quick recap.
Let's do it.
The core idea. These reactions aren't random. They're determined by the carbon type and the conditions.
It's a decision tree.
Ask yourself, is it a direct assault, SN2, a siege, SN1, or an escape tunnel, elimination?
And look for the signs. A precipitate means substitution. A sweet-smelling gas means elimination.
And the one revision tip to write on a sticky note.
It has to be this. Primary equals SN2 only. Tertiary equals SN1 or E1. Secondary is the tricky one where conditions decide everything.
Primary is fast, tertiary is slow or eliminates, and secondary is the wild card.
You got it. That hierarchy solves most problems.
Perfect. Now, I want to leave our listeners with one final thought. We've talked about how we can force these halocanes to react. But what if we put a halogen on a benzene ring, a halorine?
Ah, now that changes the game completely.
It does. These substitution reactions, they just stop working. You can boil chlorobenzene with a strong base and nothing happens.
It's incredibly stable.
So the question is, why does that ring refuse to play by these rules? Why is the fortress of benzene so much stronger?
Well, that is a fantastic mystery for your next reagent session. It involves resonance and the nature of the bond itself, a whole new story.
It is indeed. Thanks for listening to the Deep Dive. Good luck with your studies and keep visualizing those molecules.
Goodbye and happy learning.